So, good afternoon and welcome to this week's installment of the joint Heidelberg Astronomical Colloquium. We are continuing with the discussion of stars, and we will hear about a new era of stellar physics from Matteo Cantiello. And as always, the host will introduce the speaker. So I hand over to Fabian Schneider.
Thank you very much, Ralph. And it's a great pleasure for me to introduce today's speaker, Matteo Cantiello. So Matteo, as you already see from his slides, is a specialist on the evolution and also the death of massive stars. He is one of the MESA developers, and if you have never heard MESA, this is an open source stellar evolution code that is extremely successful in our domain at the moment. Matteo started to study in Pisa and got his bachelor and master degrees from there, and then after went to Utrecht to receive his PhD. His PhD supervisor was Norbert Langer, and he got his PhD then in 2009. From there on, he moved on to Bonn as an Argelander fellow for a couple of years, working as a postdoc in Bonn, and then left Europe to the US and ended up in Santa Barbara, in the beautiful Santa Barbara, working at the Kavli Institute as a postdoctoral fellow, and also a couple of years later moving on to a specialist role as meaning just a staff kind of scientist at that institute. At some point he decided to move from west to east, and now is on the east coast in the US. He's based at the Center for Computational Astrophysics at the Flatiron Institute in New York City, and is also a visiting researcher at Princeton University. And well, the stage is yours, Matteo. We're all looking forward to your talk. Thank you
so much, Fabian. Good afternoon, everyone. It's a pleasure to be here in Heidelberg. This is my second time in this beautiful city. First time was many years ago, and I only spent like 1 day, so it's good to have the chance to see this place a little bit better. And today my job is to tell you a little bit about this, what I call the new era of stellar physics. So this is going to be a talk about stars, and I'm going to tell you a little bit about how do we model stars these days, so that I can introduce the concept of this new era, why I consider a transition in our way of studying stars happening right now. Finally, I will talk about a number of frontier problems in stellar physics, in particular rotation, stellar magnetism, and evolution and muscles of massive stars. All problems that are still open, and they're dear to my heart, things I worked on in the past few years. So let's start with the basics. What is a star? You all know this is a self-gravitating ball of plasma. In a star, every point, the gradient in pressure is balanced by gravity, and so that's how you achieve hydrostatic equilibrium. Other forces in the large majority of stars, and for other forces here I mean centrifugal forces and Lorentz forces associated with magnetism, are usually very tiny perturbation to the stellar structure, so they don't really matter as compared to the gradient in pressure and gravity. There are very few exceptions to this rule, but this is usually the way we model hydrostatic equilibrium in stars. And then we can imagine that when we do study the life of stars, we have to deal with a number of timescales. So I'll start talking about the three most important timescales that you have to deal with when thinking about stars. The first one is the dynamical timescale, which is nothing else than the time it takes for a star to reassess its hydrostatic equilibrium. So if you perturb the star and the timescale on which it reacts to such a perturbation to restore its dynamic equilibrium, hydrostatic equilibrium, is the dynamical timescale. It's very short. You can think about it as the time it takes for a sound wave to propagate through a star. For the sun, this time is minutes to an hour. The other important timescale, thermal timescale, which is the time it takes for a thermal perturbation to be brought in equilibrium. So it's the time it takes for a star to react to perturbation of its thermal equilibrium. It's also the time scale of contraction of a star if the energy generation via nuclear burning is all of a sudden terminated. So this is the time scale that is involved in a transition from one burning of certain fuel to another. This timescale is longer than the dynamical timescale in most cases, especially during the main sequence, so when the stars are burning hydrogen in its core. The timescale, for example, for the thermal relaxation of the sun is of the order of 15 million years. So you can see that this is a much, much longer time for the evolution of the star. Finally, the longest timescale usually associated with stars is the nuclear burning timescale, which is the time it takes for fusion to go through some of the species that it's participating to the burning of nuclear fuel in the core. For example, during the main sequence for the sun, this is hydrogen converting to helium. And this timescale is fairly long, it's about 10 billion years for the sun. So the hierarchy of timescale from longest to shortest usually goes this way: nuclear, much longer than thermal, which is much longer than dynamical timescale. So you already see there's a very, very specific hierarchy of these timescales. And so if you want to study stars, you kind of have to deal with this hierarchy. And then, why would you want to do this? Because, well, actually, stars are very important. They are universe building blocks in a certain way. They drive ionization and chemical and dynamical evolution of gas, and they're responsible for the formation of compact remnants like neutron star and stellar black holes. Their explosion can be used to measure distances in the cosmos. And finally, we know now that they host planets. So not only the sun, but in average, every star in the universe hosts one planet. So if you want to understand your planets, you better understand your stars. So this is obviously something now is part of this high precision stellar physics, meaning that we want to understand things like the radii, the ages, and the activity of stars very well if you want to characterize exoplanets. If you want to understand reionization, stellar feedback, and chemical evolution in galaxies, massive stars in particular are very important. They dominate these processes, and so like a young like population of stars and star cluster do drive the dynamic of the ISM and its composition. Finally, we live in the era of gravitational waves, and we're now able to detect them. And all the black holes and black binaries and neutron star binaries that LIGO has detected so far likely come from these massive stars progenitors. And so understanding how these objects formed, to understand that, we need to understand the life of their progenitors object. Okay, so this is not something that maybe it's a new concept in a sense, the fact that stars until maybe a couple decades ago were kind of considered a solved problem in stellar astrophysics. So people thought, okay, we have this one-dimensional models, which I'll introduce in a second, and we are able to study the life and death of these stars to a sufficient precision for all our purposes. This is particularly true in the US, less so true in Europe. I think Europe have been more careful with this understanding. In the US, definitely, this problem was considered solved. And this was only until recently when new observation unveiled the fact that actually we do not understand stars to the precision level that we need. Some of this data coming from observations include transient surveys, which have unveiled a number of explosion and final outcome of stellar evolution that were not predicted. We're also engaging with this high precision photometry and astrometry, thanks to what we call the era of high precision stellar physics, with telescope orbiting in space, including Kepler, the Bright Constellation, Gaia, TESS, and in the future Plato. So high precision photometry, high precision astrometry, allowing us to measure properties of stars at a level that shows the shortcomings of our models. So I mentioned 1D stellar evolution. This is probably something that you either heard about or engaged with. These are models that allow to evolve stars on the long time scale of stellar evolution and nuclear burning under certain assumptions, which are pretty simple. In particular, the one-dimensional approximation, which assumes that in general you can maintain an approximation where star, which is most cases a spherical object, is well mixed on what we call horizontal surfaces. And so you can imagine the star made of shells, each shell having a same homogeneous composition and properties including rotation, for example, and density and pressure. And so at any shell, you can assume that those values can be calculated and associated with microphysics, where we usually plug into code in some approximate wave coming, for example, from table for opacity and nuclear reaction rates. But again, you can see that this way you can retain one-dimensional approximation for a star, which simplify the computational substantially, as I will show you. Now, one-dimensional cell evolution entered recently a mature phase thanks to community-driven open-source software codes. One case of this is Mesa, and I think that allowed more and more people to enter the space and work on the evolution of star, running their own models, reproducing models of other groups. Now, why am I telling you this, and why am I bothering you with one dimension? Obviously, we know this is wrong. It has to be. Stars are three-dimensional objects. So why don't we just go and simulate them in 3D and call it a day? This is a question I get asked a lot, so I thought about spending a few minutes explaining the computational challenge in doing this. So if you take a star like the Sun, and we want to simulate the whole convection, for example, in the envelope, the whole process going from the scale of energy injection, to the scale of the largest eddies that are associated with the stirring of the plasma in a convective region, down to the dissipation scale, which is a scale where viscous forces start dissipating, and so you have this cascade of motion from the large inertial scale, large injection scale to inertial scale, down to the diffusive scale. In some approximation, this could be considered a Kolmogorov spectrum of energy cascade in the star. And so the ratio between the largest scale and the luminous, the smallest scale in the Kolmogorov spectrum is associated with the Reynolds number of the flow to the 3/4. Now the Reynolds number in a star like the Sun is very large. It's over order of 10 to the 10, 10 to the 11, which means that if you want to simulate such a system in a direct numerical simulation, meaning that you want to resolve all the scales down to dissipation length, then you need to have something like a hierarchy of length scale of order of 10 to the 7, which means that your computational domain needs to include something like 10 to the 22 resolution elements. So this is a very large simulation. In fact, it is much larger than what we can do at present time. Even with the largest petascale class computers nowadays available, the type of simulation that one can run is of the order of 8,000 cube or so, which means that we're still about 10 order of magnitude away from where we need to be to run this simulation. Now, obviously, you might say, well, it's just a matter of waiting some time. Computers get faster all the time. In fact, there's this thing called the Moore's law that tells us that computers get faster. They double in speed about every 1.5 years. And so this is showing this scaling here, the number of transistors, so computational power, if you want, as a function of time. This law has stuck pretty well until recently. There are discussions why this might actually not continue in the future. I'm not going to talk about that. But this plot is showing a few trends that are maybe interesting to analyze here for a second. The frequency clock of your processor in your computer hasn't really changed in the last 10 years or so. We're at a few gigahertz and we're sticking to that. What has really compensated for this, to allow for this growth in computational power is actually the number of logical cores that now you're packing in your laptop, for example. It's typical to have 10 logical cores in your laptop, and that's a trend that is continuing. There's discussion about, if you want to extrapolate this longer, there's also issues with how much computing power, actually in terms of really energy you're going to suck, but that's a different discussion. So, let's say we can assume that this will continue. How long it will take, assuming this is the way we do things in the future, before we can run a direct numerical simulation of a star like the Sun? Well, so it's 1.5 times log 2 of 10 to the 11, which is the number of the gap we need to cover, and this is about 55 years from now. That's a long time. Now, obviously, it's not
is worse than that, because that's only the time it will take to run the simulation on a dynamical timescale, which we remember is much shorter than the other interesting timescale for stellar evolution, the thermal and dynamical and the nuclear burning timescale. If you want to run the sun for its own lifetime, then you need also to add the fact that you're going to have to run about 10 to the 15 time steps in this massive grid that you created. And so that means that you'll have to wait even more to be able to reach that type of capabilities. And we're talking about things like hundreds of years from now. Now, obviously, this is a simplified outlook where I'm assuming that this is the way we're going to do things in the future, which might not be the case. There might be advancements in both hardware and algorithms. And this could just substantially reduce the timeline. So I think it's important to keep an open mind about this and keep an open mind about future ways that we might go in terms of solving things like Navier-Stokes equations. There's a lot of groups thinking about machine learning approaches to doing this. But I think for now, this is motivating the reason for still using one-dimensional models and occasionally using simplified three-dimensional simulations that are not resolved down to the diffusion scale to understand stars. And so the thing I just said is that basically models are still useful. And because even if we cannot run simulation of stars resolving all the scales involved, it might still be, especially in hydrodynamics, that some of the flow features that are captured by not fully resolved simulation are still useful to understand the real stellar evolution case. So some of the results might still be robust and useful to understand astrophysical situations. Particular attention, I think, should be placed in understanding when we do MHD calculations. And the reason is that magnetic fields has this habit to sometimes emerge from small scales and connect to larger scales. It's called inverse cascade. And if you have an inverse cascade, you never know, if you're not resolving the smallest scale, if something like that might happen. And so maybe you don't see certain properties of the flow because you haven't reached a resolution high enough to see this dynamo operating and connecting to the larger scale and changing completely the properties of the flow. So anyway, that's just to say that every time you see an MHD calculation, let's take it with a grain of salt, because in this not fully resolved simulation, there could be surprises when we move to extrapolating to higher Reynolds number and magnetic Reynolds numbers. Okay, so a new era of stellar physics is the era in which we live in, and I think this era is at the nexus of a synergy between the high precision large data sets that I was talking about, coming now mostly from space, the one-dimensional calculation that entered this mature stage where codes can be used and people can test against each other using open source approaches, and ultimately these multidimensional models, which even if not fully resolved, can now be run routinely and used to determine at different places in the evolution of a star properties of the object that maybe we know they're not fully captured in a one-dimensional approximation. And so this is, in a sense, you can imagine this as a loop between these tools and data sets that can allow us to make progress. And so this is some of the things that we like to do at CCA. This is, you can see here the stellar evolution track with 1D code of a 15 solar mass star. This is a massive stars. And we've been looking at different parts of the evolution with different codes that are can be used to study different processes, to understand different questions in the physics of convection, for example, excitation of intergravity waves, mass loss, and other problems. Okay, so let me move into some open questions in our study of stars. And then we're going to start with internal rotation and magnetism, which are interesting processes that are important to understand in the final outcome of stellar evolution. And I'll start with the fact that internal rotation and internal magnetism are two very difficult problems because they usually been hiding inside stars. It's very hard to measure the rotational profile of a star or even the magnetization of its core. And until some time ago, actually people thought this would be impossible. There's a famous case of Eddington in 1926 said that it would seem that the deep interior of the sun and stars is less accessible to scientific investigation than any other region of the universe. It turns out it was proved wrong in the sense that recently we've been able to actually study these very regions with a new tool that came from the observation, photometric observation of stars from space. And this is thanks to asteroseismology. So I'm going to spend some time talking about asteroseismology, which is the study of wave propagation and excitation in stars. Okay, so I'll focus on one specific type of pulsation of star, which are called solar-like oscillations. As the name suggests, these were first observed in the sun. And these are actually sound waves that are excited by turbulent convection in the envelope of the sun. The analogy is what happens when you boil water in a pan in your kitchen. You can actually tell that the water is boiling even if you're not in the kitchen. In fact, you will hear some noise at some point coming from the fact that the water is boiling and producing sound waves. So the turbulence is actually exciting sound waves that propagate in the air. Now the scale, obviously, for the sun is different. Each convective cell is the size of California or so. So these are like, movement that happens on much longer time scale, which turns out on frequencies of oscillation are much, much lower. As we will see, these are from minutes for the scale of the sun to hours, weeks, and even months for more evolved stars. Okay, so before Kepler and Corot, some days of the telescope doing photometry from space, this was the situation in terms of how many stars we knew that were showing this solar oscillation other than the sun. With Kepler especially, the situation changed substantially. And you can see here, as function of the on an HR diagram, so log temperature versus luminosity, for stars in the range 1 to 2.5 solar masses, the number of detection of solar-like oscillations and their amplitude in part per million detected by Kepler. So thousands and thousands of these objects were seen. And you can see an interesting straightaway feature is that as you go on the red giant, so there's the main sequence down here, and you have all on the red giant as the star expands, the amplitude of this oscillation gets larger. And that's because the luminosity of the star is also larger. But still, you can also see why this needed to could only be done from space. The size of this oscillation is very small. Is a few tens to a few thousand parts per million. So it's something that is completely overwhelmed by the atmosphere if you try to do this from the ground. That's why you need to go to space. Okay, so I'm going to show you this is the most technical chart I'll have, and it's the only one. But it's going to be useful to understand the little bit of asteroseismology that I'll talk about in a second. This is a propagation diagram, which is a tool used in asteroseismology to understand how waves propagate in the star. And you can think about this as trying to understand the star as a musical instrument, okay? So on the x-axis, you have a log of radius of the star. On the y-axis, there's some characteristic frequencies that I'll tell you in a second what they are. So the first frequency I want to introduce is the lamp frequencies, this blue line, which is pretty much the inverse of the sound crossing time. It tells us pretty much the time it takes for a sound wave to propagate through the star. And in fact, if you perturb the star in the envelope, sound waves usually propagate down to this blue line and bounce back. And that's create what is called the P-mode cavity. So for example, this new max line here is the typical timescale associated frequency of the turnover timescale in the convective envelope. So you can imagine things get excited at this frequency in the envelope, so sound waves will propagate in this region of the star. Now there is also G-mode cavity, where actually, and sorry, the P-modes or sound waves, the force, the restoring force, is the gradient in pressure. Inside this red line, which is called the Brand-Vasila frequency, which is pretty much the frequency of a parcel of plasma that is disturbed from its hydrostatic equilibrium. So if you take like a piece of plasma and you move it down a little bit, that it wants to oscillate around its equilibrium position, it does it with the typical frequency, which is similar to the Brand-Vasila frequency. So it turns out that these red lines it's creating a cavity where actually G mode, so waves that are sustained by buoyancy, can survive. And those can live in this region. So it turns out that in a star evolved after the main sequence, like the sun, when it becomes a red giant, you can have like excitation of a P mode in the envelope via turbulent convection. And then some of the energy can actually leak into the G mode cavity. This is really akin like some tunneling effect in quantum mechanics, where a little tiny energy from this mode can penetrate and actually start exciting on certain timescale these G modes to propagate. And you can have what is called a mixed mode, which is an eigenfunction in the star made of a piece of P mode, some evanescent component, and a G mode in the core. So why am I telling you this? Why this is interesting? Well, because this eigenfunction, in a sense, is bringing to surface some knowledge, some information from the core. How so? Imagine that you have two different mixed modes, one that has more inertia in the core and one has more inertia in the envelope, meaning that one is able to propagate more in the core and one is able to propagate more in the envelope. So spending more time in one part of the star or the other. Now imagine that now a star is differentially rotating. So the core is rotating faster than the envelope, which turns out to be the case for some of these stars. Then the splitting of this mode, which is introduced by the fact that it's rotating, it's really like a splitting and a breaking of the symmetry of some of these modes, can tell you differential rotation if you compare the splitting in these different modes, one P mode and one G mode dominated. So this is a way to measure differential rotation in stars as evolving, which is a big deal, and it's something that's been done routinely now by different groups, for example, Benoît Mosser group in France, measuring the rotation rate as function of the evolution of these stars on the red giant branch. Why is this interesting? Because, as I'll say in a second, allows you to measure, for example, the coupling between core and envelope as the star is evolving. And so it can help you telling something about processes, hydrodynamics or magnetohydrodynamics processes that connect different layers of the star in terms of rotation properties. So let's look at this plot and just focus on this group of stars. Forget about this for a second. This is each cross is a different star, and you can see its radius as a function of the x-axis. So these are stars that tend to be more and more evolved, going to the right. The sun will be down there here somehow. These are all stars more evolved than the sun. And this is the period of rotation of the core. Now remember, this star is a red giant, and red giants do have a contracting core and an expanding envelope. So if there was no angular momentum transport, what you expect is that the core will spin up like a ballerina very rapidly. Actually, what you see here is the opposite. The core is not spinning up, it's actually slowing down slightly. So this is really strongly support the notion that some level of angular momentum transport is occurring at actually pretty efficient rate, so that the angular momentum is transported out from the core into the envelope, and the envelope is just expanding as a fairly solid, as a big body. It has a lot of inertia. Okay, so the idea of angular momentum transport in stars is something that we had for a long time, and people have worked out different classes of mechanism and introduced some of this into 1D stellar evolution calculations. You could imagine that shear mixing in the radial direction should be important. There are like circulation induced by the fact that rotating stars tend to have like an imbalance in temperature between the pole and the envelope. This is called the von Zeipel effect that leads to some large circulation that occur on some thermal scale, thermal time scale. And then there are like magnetic effects due to the fact that if you have a magnetic field in a star and you have differential rotation, you can twist the field until you have some restoring force associated with the torque that is due to the stretching this rubber band, so to speak, into the star. And finally, internal gravity waves can also transport angular momentum. I'm not going to talk too much about this, but internal gravity waves are these waves that are excited also by turbulent convection and can transport and dissipate angular momentum in different parts of the star. So different classes, hydrodynamics instabilities, rotational induced circulations, magnetic torques, internal gravity waves. And these were introduced in one-dimensional calculation because, well, this shallow approximation that I mentioned at the beginning, because every shell in this approximation is supposed to be homogeneous in composition and angular momentum. So it's possible to approach the problem as a diffusive problem, for example. So we checked a little bit how this prescription that we had in codes for decades will compare to the observation that now we have of stars evolving on the red giant. So here now again we have log period of rotation on the y-axis and evolutionary radius of a star on the y-axis, on the x-axis. And you can see that the black line is show the evolution of the envelope, so the surface rotation rate of the star. The star actually is slowing down substantially as r squared. This is expected as the envelope has a large inertia. And then these are different lines showing different assumptions for angular momentum transport. So the green line is assuming angular momentum conservation. So no angular momentum transport, and this is what you will expect from the ballerina effect by spinning up the core as it contracts. The core should spin up very, very rapidly as it climbs the red giant branch. You can see like 10 to minus 2 days, very fast. If you add like angular momentum transport due to hydrodynamic effect, you do transport some angular momentum, but not much. The reason is that this phase evolution is fairly fast compared to the time scale of these angular momentum transport processes. However, if you have these magnetic torques in the Sprue-Tayler dynamo formalism, which is something I'm not going to go into details, but has to do with this winding up of magnetic fields from the differential rotation, then you can do a much better job. How does it compare to observations? Not very well. So the observations show that actually the torques that we require to explain this data is actually much stronger. So this pushed like people to go back to the blackboard to try to understand this result. And recently there was some advancement from Jim Fuller's group and Tony Pyro and Adam Germain, who's now at CCA, revisiting these Tayler magnetic torques, finding a new criterion for the saturation, and they actually find out that they were able, with this new prescription, to potentially reproduce observation of core rotation on the RGB, on the clump, which is when the star later on burned helium in its core, and even for the white dwarfs. So kind of like interesting revision. I think it's still debated if this is the right one, and people are still comparing this observation and also numerical calculations. So I think the jury is still out, but this is progress. And obviously, once you have this type of understanding, the hope is that we can port it to more massive stars. Obviously, this is done in the low mass regime where we can do this observation for low mass stars in asteroseismology. Unfortunately, in massive stars, we're still not there in terms of understanding their rotational properties with asteroseismology. But if you port the same physics, then you can hope to calculate the final rotation rate of things like black hole produced by massive stars. This is an example showing the final Kerr parameter of single stars using this Sprue-Tayler dynamo torques in the Fuller, Pirro, and Germain new prescription. And you can see that the Kerr parameter of these stars tend to be very small. So the rotation rate of this black hole at the end of the evolution should be very small. There's some exception if you have some binary mass transfer, you can spin them up. And then you can compare them to observation from LIGO. And you can see that, yeah, maybe there is a way to explain some of these, but there are also, LIGO is also observing some black hole spin to be fairly large. So I think that's, pushing us to think a bit harder about what kind of evolutionary channels are involved into producing these massive black holes. Again, some of the observation, I don't know if you go there. Okay, so an interesting puzzle that came our way, still involving these mixed modes that I just introduced, was this puzzle of depressed dipole mixed modes. So let me tell you a little bit what this was. So in 2015, Dennis Stello came to KTP and showed us this plot. This plot showing the power density as function of frequency of the oscillation spectrum of two stars that are identical on the HR diagram. Okay, so what I'm showing here, this combo of modes these are like the solar-like oscillation excited in the turbulent convective envelope of these red giant stars. You can see that there's different degree L of oscillation. So L equals 0 is the radial oscillation modes. L equal 1 is dipole, L equal 2 is quadrupole, L equal 3 is octupole. And you can see that they're excited at different amplitude. But the interesting thing is that between those two Kepler target, the L equal 1 modes are around the same frequency, and the fact that the frequency is the same, and you can see the frequency, as I told you, is telling you that this oscillation occur on a time scale of weeks or so. It's all very slow, so you need to observe these things for a long time. In the case of Kepler, 4 years to get this beautiful spectra. But you can see that the spectra looks almost identical, except that the L equal 1, the red modes, are very depressed. And so it was puzzling, why is the case? What's happening in the star that is able to do this? Is able to depress the L equal 1, but not L equal 0? Well, it turns out that something I haven't told you is that the L equals 0 doesn't couple with G modes. So the L equals 0 only lives in the envelope. And the L equal 1 are actually the one that can connect most efficiently to the core, because they can couple with the G modes. G modes that don't exist at L equals 0. You can only have them at L equal 1 or L equal larger than 1. So we knew straight away that something was happening in the core of these stars. And something is different in the core of this object compared to this one. The working hypothesis was that maybe there was some magnetic field hiding in the core that is able to perturb and depress the mode that we are observing. So the idea was that in the presence of a strong magnetic field, the magnetic tension associated with the Lorentz force might be able to perturb and disturb the propagation of the G mode. So if you remember how a G mode propagate, I don't know if you have seen, but what G modes mostly propagate horizontally. So they displace the plasma mostly horizontally. So if you have a magnetic field line in the core of the star, let's say radial, and the G modes arrive, what it's trying to do is trying to stretch the magnetic field line in the horizontal direction. So you can imagine that if the magnetic field line is weak, meaning that the Lorentz force associated is smaller than the buoyancy, then nothing really happened. The field stretches a little bit the magnetic field, and then it goes back, and all is fine. But you can imagine there might be a critical magnetic field when the magnetic tensions, Lorentz force, becomes comparable to buoyancy. At that point, something must happen. And you can actually calculate that magnetic field strength, and it's pretty simple, and it's a function of the Brandweisseiler frequency, as you might imagine, the density, and the frequency of the wave. This critical field turned out to be, for this star, of the order 10 to the 5 Gauss. So 100,000 Gauss. And what happens when that occurs is that actually the G modes are actually turned into Alfvén modes, or magnetoacoustic waves, but mostly magnetogravity waves. And so this happens at typical critical field of 10 to the 5 Gauss. And once that happens, these waves are trapped and they dissipate in the core. They're not able to make it back into the envelope and reconnect to the P mode. So the P modes at L equal 1, which are the one that talked most of the core, they continuously leak energy in the core that never gets back. And that creates the dissipation, this depression that we observe. Now, this was interesting, but could we test this idea a little bit more, and what kind of consequences will this idea have for the observation? A second clue came from looking at the distribution of masses of this object that we were seeing depressed. So I only show you 2 objects at the beginning, but it turns out that a large fraction of the red giants that Kepler is observing show this depression. And this is what I'm showing here. This is a plot of, again, the frequency as function of, frequency on the x-axis and visibility square, which is a measurement of mode energy for the L equal 1 dipole mixed modes as function of mass. So you can see the mass going from 0.9 to 2.1 solar masses. It's possible to do this because Asteroseismology has scaling laws that allow you to determine the mass of the star. And you can see that at low mass, less than 1.1 solar masses, the visibility square is almost constant for all the star. But as you go to higher and higher mass, there is this branch of depressed star here that is actually getting larger and larger as a fraction. This black line is actually the prediction of where the depressed mode should be in the assumption that all the energy leaking into the core stays in the core. And you can see that matches pretty well the location of these depressed dipole mode stars. Now the interesting thing is that if you assume that each of these stars here is now a star that has a strong magnetic field in the core, more than 10 to the 5 Gauss, and we plot this as function of mass, we got this interesting landscape. So here is a fraction of stars that now interpret as strongly magnetized as function of their mass. And you can see that this is a growing function of mass with a cutoff at about 1.1 solar masses. Now, if you remember stellar physics, stellar structure 101, you remember that at 1.1 solar masses, there's a transition during the main sequence. And remember, these are these are red giants, descendant of main sequence stars burning hydrogen in the core. There's a transition between stars that had radiative core or convective core above 1.1. So the sun is in this region, radiative core. And in fact, the descendant of stars with the sun, like the sun, they don't seem to have magnetized cores. But stars that have convective core to the main sequence do have strong magnetic fields with an increasing rate up to 50% in the core, in excess of 10 to the 5 Gauss. So what is going on here, we believe, is that some dynamo action is going on during the main sequence in the convective core of these stars. At the end of the main sequence, this magnetic field, the magnetic flux, is able to establish itself in a stable configuration. This stable configuration have been studied. There's an understanding that you can obtain them if you interlock poloidal and toroidal fields together. And the equipartition field that you expect in the convective core of this star is actually of the order of 10 to the 5 Gauss, which is very similar to the value observed. Obviously, flux conservation as the core contracts a little bit will give you a factor of 10 or 100 more on the red giant. So, this lower limit that we're observing is consistent with these observations. And so I think that that's the story that is told here by these observations. And so does that potentially have impact for the evolution of star in the sense that if every time we have a convective core, we're able to create some strong magnetic field at the equipartition level, and then some of these magnetic fields can assemble, organize themselves into stable configurations, then eventually you will consider this magnetic field to be conserved through cell evolution, potentially even down to the terminal evolutionary phase of the star, potentially even able to explain some of the magnetized white dwarf and even neutron star magnetars. So John, I want to conclude this first part on asteroseismology. So asteroseismology allowed us to probe the interior of stars and potentially shed light on our understanding of rotational and angular momentum transport processes, and also the way that magnetic fields might be generated in stars and how they can actually be present in further down the road in stellar evolution. And just to note that this magnetic field are currently not included in any stellar evolutionary models, so they might have an impact for a star, and in particular for angular momentum transport. Again, there's a feedback loop in a sense between these two areas of investigation, because large-scale magnetic field can also be important in transporting angular momentum. Okay, I'm gonna switch gear and spend the last 10 minutes talking about massive stars, but any questions about this part? If not, I can take question at the end. Okay, yes. Yeah, so I think that there is work in, so Jim Fuller has published a paper where we try to reproduce the final spin of pulsars, and I think that with this revised Sprue-Taylor dynamo, you can actually end up in the right regime where pulsar, non-recycled pulsar, but normal young pulsars are observed. So this seems to be ballpark correct. Okay. I'm going to talk now about massive stars, because I'm very passionate about massive stars. These are very important if we understand, again, the final outcome, neutron stars, black holes, and also understanding, things like luminous blue variables, stars that are wrapped low material, and obviously there is a. This is my personal laundry list of what are the most uncertain piece of physics for understanding massive stars. Obviously, rotational magnetic fields also important. We discussed them in the first part of the talk. And then there is a binary interactions. This is actually very important because you probably know that most massive stars are found in multiple systems, and so their ability to interact with themselves and in the companion is going to change their evolution substantially. There's a lot of people working on this problem, and what I'm trying to say here, the reason why I'm not right now focusing on this, is that after a star interact in a binary system, they're actually gonna leave a single star for a large part of their story. And so I think that if we don't understand the physics of single stars, then there's no way we're gonna understand this more complicated evolutionary phases associated with binary interaction. So I'm gonna focus first on basic physics in single stars, that then say once we get this right, we're going to move to binary interaction and plug those things in. So in terms of understanding of the structure of massive stars, I think that it's clear that we do not understand exactly how their envelope structure works and how they lose mass. In particular, mass loss for massive stars is a big source of uncertainties in our models. There's three types, I would say, broadly speaking, of mass loss in massive stars. Line-driven winds. These are actually the winds that you see or you expect in hot stars. These are driven by lines, so it's like resonance lines at the surface of the star in the wind, and they interact with the photon fields, and they can accelerate material. And actually, we understand those winds fairly well, theoretically. And I would say down to a factor of 3 in terms of the final mass loss rate that we predict. I think this is uncertain, and it's pretty good in astrophysics, I would say. This uncertain come from wind clumping, which is the level of, if you want, of perturbation and non-spherical approximation in the wind flow. These winds are metallicity dependent because actually it turns out that they mostly rely on resonant lines, and so they're very dependent on things like iron in the wind. So if you have more iron, the more you drive them. And so going down to lower metallicities, those winds become weaker and weaker. But stars actually lose a lot of mass on the red supergiants, where we have these cool red supergiant winds, which are poorly understood theoretically and also poorly constrained observationally. We don't even know if they're metallicity dependent or not. And finally, we do know that some stars actually go through some continuum-driven winds or even eruptions when they're in this region of the HR diagram in the blue, where they call luminous, just due to this interesting phenomenology where they seem to shed material at a higher rate, and we don't really know what's the process driving them, so it's not understood theoretically. Some of these massive stars that I'm going to talk about, and the reason why we don't understand the energy transport in the envelope, has to do with the fact that if you know how energy is transported in stars in 1D, you probably heard about mixing length theory. Mixing length theory is this approximation of an hydrodynamic process that we use in 1D, where we assume that a convective element is a parcel of plasma that is moved about a pressure scale height in the star and release its heat energy excess. And so this approximation works as long as your like piece of plasma is not leaking out too much energy as it moves in the star. Now, in this situation of these massive stars, where you can have convection close to the surface, some of the diffusion timescale for the photons outside of the blob can become comparable to the advection timescale of the blob itself. Meaning that if you're carrying like a bucket full of water, but your bucket has a lot of holes, at the end of your pressure scale height, you might not have any water in it, so you haven't transported much of the energy. So this kind of a leaky convection is typical of a situation where your radiation field is very intense and you're close to this critical optical depth, which is an optical depth where the radiation diffusion timescale becomes comparable to dynamical timescale. In this situation, mixing length theory is not supposed to work. In fact, one thing that you get is that the MLT trying to drive convective motion to velocity close to the sound speed, but at that point, you lose one of the key assumptions of MLT, which is pressure balance between the blob and the outer region of the star. So in this situation, MLT fail, and this is one of the situations where you want to start studying the problem with a three-dimensional model where you include radiation and hydrodynamics. If you want to do that, you also need to care about opacity. The opacity of stars is like mostly electron scattering in the deep hot layers, but as you move closer to the surface, you have this recombination of different species that drive opacity peaks, for example, associated with iron, and then helium and hydrogen. And this is showing as function of the temperatures of getting closer to the surface of some of these stars, these opacity lines. And these are as function of density. So you're fixing the temperature, you're fixing the density and moving at temperature, and you can see that if you have different densities, you can have very large variation of the opacity. Something that will be useful to understand results in a second. So let me close up talking about this 3D radiation hydro calculation that we run to understand mass loss and stability in massive stars. Just to remind you a little bit of star structure, I could have showed this earlier, but remember, stars are fully convective at low mass in the K and M spectral type. They start having just a convective envelope for stars like the Sun. And then as you move to higher masses, to the early type stars, you start having convective core. This is due to the fact that you're burning CNO, burning hydrogen via the CNO cycle, which create a steeper temperature gradient. And then you have this ion convection zone developing close to the surface. Now in a 1D model, this ion convection zone is below the surface. This is what we see if you run a MESA model of any other model of 1D stellar evolution. And then we try running this with 3D radiation hydro, so Athena++ in spherical geometry using variable adding tensor, solving the full time dependent radiation transport equation, and coupling the code with full opacity. So now the code can track opacity in the Rosseland mean opacity mode. And this is the result we found for a main sequence massive star, is actually that this convective region that they're well separated from the surface in this 1D models actually become very turbulent and actually affect directly the surface of the star in this three-dimensional model. So you can see here actually the photosphere of the star is very turbulent. There are velocity fields of order of 100 km per second. Actually, these velocity fields are now observed in the stars, and we believe that they're coming from these directly from this ion convection zone steering the plasma there. So just to show the type of simulation we can do, but these are very expensive models, and so we wanted to also study a little bit more objects that are a bit more evolved and more luminous to understand this process of mass loss, in particular in the context of these luminous blue variables. So what I'm showing here is the location of hot Asteroseismology stars, things like P Cygni here. These stars are in this region where they usually park in quiescence in this region, but occasionally they move in temperature at the same luminosity and enter this region where the star loses mass at a higher rate. If you try to simulate with 1D models stars in this location, you end up all over the place because different models, which I show here, the MESA model, GENEC, or Stern from different groups, they have different assumptions for the energy transport in the envelope that they try to replace this MLT, which is inefficient or not adapt to study this process. And so this model end up all over the place, and we don't really know, we don't have really a predictive power. So here we try to run large-scale three-dimensional simulation of stars in this region between the quiescent and the cool outburst Asteroseismology regions at different temperature. So I'm going to show you now a result from these three-dimensional models run with Athena. These are simulations that takes about 10 to the 8 CPU hours. So we have to run them on some of the large facilities. Particularly this one was run at Argonne National Lab. What I'm showing here is gas density in log scale. And just that you're familiar with the type of projection we're going to use, this sometimes confuses people. Imagine this is the wig of a clown. So we remove the core, which you don't need to simulate because timescales there are much longer. And we just show in the outer part of the envelope in this cutout sphere. Okay, so we start with the MESA model, and we relax it in Athena. And what we start seeing is the development of turbulent convection at the ion convection zone regions where the ion opacity peak is increasing. Then eventually we start seeing, we zoomed out now because the photosphere expanded, and we start seeing this non-steady behavior where a lot of material is actually ejected from the star. Some material actually falls back, so we expect some inverse P Cygni profile in this from some star like this. And actually, we do see a mass loss rate purely from continuum-driven winds in this case at the level of 10 to the minus 5 solar masses per year. This is not even including line driving, so this could be higher if we're including that. And this is in steady state. Now, this is great, but what's actually happening here? What is really the physics driving this interesting plumes and non-steady behavior of the simulation? So, yeah, and we claim that the mass loss rate and the phenomenology we're seeing here can reproduce the location and mass loss property of some luminous blue variables during the outburst. Now, what is going on in the simulation? Well, remember this important plot about the opacity. What's going on is, we believe, is that at this region where you have the ion convection zone driving turbulence, the turbulence is driving density fluctuations. So this density fluctuation propagate right higher up in the star where the temperature is lower and where the helium recombines. Now the issue is that the star is already close to the Addington limit, okay? But if you're close to the Addington, imagine the Addington luminosity is down here. Depending on which opacity track you are, you might be super Addington or sub Addington. So if you have large density fluctuation horizontally on the horizontal surface, like a blob that is over dense might be on this high opacity branch of the opacity curve and might be accelerated above gravity. So that blob might be a super Addington, while another blob that is like down here, lower density, might not. And so this is actually creating this like structure of blobs and plumes that are ejected from the star in this non-steady behavior. And this has to do exactly with the turbulence excited by ion down here propagating into this region of helium recombination where the opacity depends so strongly on the density. Just to convince that we reach steady state in the simulation. And we're able actually to observe using this, create light curves from this simulation. For example, for this model I just showed you, you can see that the light curve prediction for this object is a variability of actually of almost a magnitude on time scale of weeks. While if you look at the models that are in quiescence, which we run, I didn't show you, but they're much more quiet. The mass loss rate that we observe there is like at least an order of magnitude smaller. The variability is much smaller, 20% in photometry, but the time scale are also longer. So is this something that we can test observationally? Yeah, actually we can. And so this model that I showed you initially, it's actually at the same location and temperature as P Cygni, which is like one of the stars in the class of these LBVs and Asteroseismology variables. And this is an observation from bright constellation from space showing like variability both in time scale and an amplitude similar to the predictions for our models. So to conclude, massive star evolution is still very uncertain, even for single stars, so we still need to understand basic processes like energy transport in the envelope of this object, which has impact on for things like radius and mass loss. And we're able to run the first 3D global radiation hydro calculation to study stars in this region of instability called LBVs. And so we believe we've made some progress in understanding this class of objects. And I'd like to thank you for your attention and take questions now.
Many thanks, Matteo, for
of course.
This very nice overview of what we know about stellar evolution, its complexity, and the challenges that we are facing. And of course, the implications for many other fields of physics. So, questions?
Yes, okay. Yes, so the question is, what is the mass range of the models we've been running for these massive stars models? In which evolutionary phase? and in case if we consider or we study the pair instability, pair position instability process. Okay, let me go back to the HR diagram to explain this a little bit. So the models that we run were models evolved, models of a 60 Solon mass, the one I show you, around the 60 Solon mass, evolved during the main sequence toward the end of the main sequence. And so such that we enter this region of instability, or at least where instability is observed. It doesn't really matter too much what the core is doing for the star, as long as your model has the luminosity and temperature of the observed objects. That said, it's an interesting question. What are these objects? How do they get there? Are they, burning hydrogen in their core, or they're burning helium and returning from the left, from the right? So this model don't answer that question. But in our calculation, they were still burning hydrogen in the core. So concerning pair instability and pair position instability, obviously that's something that will happen much later in the evolution of the stars. If some of these models were able to, maybe this more massive star, were able to retain enough mass and go to later evolutionary stages, obviously they might enter pair instability phase toward the end of their evolution. But that's something that we don't need to worry about here, because the temperature of the core is not high enough for pair production. You need 10 to the 9 Kelvin to get into that region, and here we are still burning hydrogen in the core. So, yeah, of course.
So next question here.
Yeah. So I have a question. You mentioned that 1D stellar models are not very accurate because you have to take the stellar rotation into account. So naturally, the velocity of the gas at the stellar equator would be faster than the gas at the poles.
Mm-hmm.
So I want to know how inaccurate the 1D stellar model is if we take the stellar rotation into account.
Okay, so again, maybe I want to reframe so you mentioned that stellar model, 1D stellar model are inaccurate. I think that yes, and obviously being 1D, they're always going to be inaccurate, but they can be sufficient depending on what question you're trying to answer. And I think, this idea of trying to understand angular momentum transport and rotation is important if you're interested in, explaining the Kerr parameter of black holes and the spin on neutron stars and other features. So in that case, yes, we're facing these shortcomings that we still don't understand angular momentum transport perfectly. We do see stars rotating rapidly, especially massive stars already on the main sequence. Some actually are rotating so fast that you might enter a situation that maybe you were hinting at, where the equator is rotating so fast that material at the equator might actually become scientifically supported, which is an exception to that rule I said at the very beginning of the talk, where forces that are of rotational and magnetic energy, they never matter in a star. Well, there's a situation where they do, and so if a star is approaching critical rotation, then you can lose material because of this centrifugally enhanced mass loss, which is something that we include in 1D models, but we know that it's a very rough approximation. So this is still, I think, a regime of uncertainty for our models that need to be resolved.
So that means that for slower rotation stars, for example, maybe some red giants, then the 1D stellar model is accurate enough.
Yeah, so in general, if your star is far away from critical rotation, the expectation is that you don't need to care too much about rotation for the structure of the star. However, it can matter for the internal mixing, and it matters if you care about the rotation rate of the core. Even if the red giant is rotating very slowly at the surface, the core potentially rotating fairly fast or faster on the core, on the envelope. And later on, you might be interested in knowing, okay, what's the spin rate of the white dwarf that this red giant is going to produce? So if that's the question you're interested in, then yes, you need to do a good job in tracking the angular momentum transport. But for the structure of the star, you're right. Star like the sun, they're not really, you could run the sun without rotation and you predict very well the location on the HR diagram. And later on, as it's expanded the red giants, that spin, even the envelope spins even slower, so you don't really care about the rotational effect on the structure. You care more for this angular momentum transport and internal mixing.
So maybe I can intersect a question. I'm wondering about the impact of initial conditions, specifically in massive stars, and specifically about magnetic fields, because the massive stars have difficulties generating fields on the surface, right? That is at least the general view. Do you think they can be accreted from the initial cloud and survive to be observed, or what is your thinking of that?
So observationally, about 10% of massive stars, OB stars, seems to have large-scale field at the surface. What's the origin of that field? It's unclear. People talk about fossil fields, so fields that are inherited from formation process, either a dynamo in the pre-main sequence phase, or maybe, as you pointed out, some kind of conservation of part of the magnetic flux. Obviously, you cannot conserve all, otherwise you're not going to form the star. I think our understanding of the process is very primitive, especially for me. What I can say is that there might be ways for generating magnetic fields up to some level in this convective region close to the surface. The equipartition field in that case are not very high, of order of a few hundred Gauss. And so that said, I think that it's important to understand also if these fields, large-scale fields, are observed, where they come from. And I think we're still really relying at this point on the observations. I don't think there is any self-consistent model of this process, especially for massive stars. That said, we ran some simulation of this kind, including magnetic fields, to see what happened. I didn't talk much about that, but there's interesting effects where the structure of a star, as you have this radiation hydra, relies on the fact that the density fluctuation coupled to the opacity and create tunnels for the radiation field to emerge. So the problem becomes really three-dimensional in the sense that the balance between advection and diffusion of radiation relies on the landscape produced by the interaction between radiation field and the opacity, which drive the turbulence itself. So it's a very interesting feedback loop where the radiation field goes to the holes of this Swiss cheese-like and produces instabilities that lead to even more density and more holes. And we call this porosity effect. If you put a magnetic field there, the interesting thing is the field initially will be amplified until it becomes buoyant. And then magnetic field produces some pressure, magnetic pressure, which also creates extra holes and allows actually more radiation flux to emerge. On top of that, the magnetic field buoyantly also transport advectively some of the flux. So actually introducing magnetic fields increase the amount of energy transported outward and actually make the star a little more compact. So this simulation were done in a box. We haven't done the large scale with the magnetic field, where we've done the box simulations. We have the paper in 2017 where we discuss about that.
So we have a question in the chat. Excellent. Maybe you can
I can read it from Richard. I was wondering if stellar intensity interferometric imaging of the closest stars along the lines of Embry, Brown, and Twist experiments on Sirius in the 50s will also be potentially useful diagnostic, especially for surface phenomena, like surface turbulent convective zone that you mentioned. Your resolution allowed over time. Yeah, so Richard is really asking if it's possible to observe some of this structure in some of these stars. It might be possible for LBVs, some of the biggest LBVs. I know this is, interferometry is becoming, it's a mature field, and people have done some of these things for red supergiants, and even also for main sequence stars. I don't know if anyone has tried to do this for this more massive object, and if there is a reason why that's not the case. Something that is a proxy for this, and I think this is a great question I don't have honestly the answer to, but something to investigate. The proxy for this is spectropolarimetry. So people that look at the degree of polarization of light from these objects, and found out that actually LBVs do have some level of polarization which is consistent with a structure surface or massless structure around it. So having these large chunks and large plumes of material might be correlated or might create this degree of polarization. But yeah, I think it's a great question and maybe worth looking at the possibility of doing some from interferometric observations. Yeah, I think polarimetry, and some people have done it. For example, P Cygni I think shows a polarization level of a few percent, maybe 2 to 3%, if I remember correctly, which is consistent with, is marginally consistent with structures ejected at the scale of the pressure scale height of this convective region close to the surface. In particular, the ion convection zone, which drives the density fluctuation. So that story is at least consistent with the polarization observation.
Okay. Before we thank you for this fantastic talk and the discussion, we will go to bigger scales, to central black holes, and we will have a talk by Shepard-Dulemans about imaging supermassive black holes with the Event Horizon Telescope. So with that, let us thank Matteo for this very nice presentation today. Many thanks.